Hello everyone, today I will present my project on breast cancer classification using transfer learning. The goal is to assist radiologists by providing an automated and reliable second opinion system based on ultrasound images. Ultrasound imaging is widely used because it is safe and low cost, but it suffers from noise and subjectivity. In this project, I address this problem using transfer learning with a pre-trained mobile NetV2 model. With this approach, I achieved 86.08% accuracy on unseen test data. Here we see the main challenge. Raw ultrasound images contain strong speckle noise and low contrast, which makes tumor boundaries unclear. Although ground truth masks exist, the model must learn the lesion structure only from noisy input images. The dataset shows a significant class imbalance. Benign samples dominate the dataset, while malignant cases are fewer. This imbalance introduces a bias risk, which is especially critical for cancer detection. Benign and malignant lesions often share similar visual characteristics. Especially in early stages, malignant lesions may not appear aggressive. Therefore, the model must learn subtle texture-based features rather than simple geometric shapes. Previous studies show that transfer learning performs well on medical datasets with limited samples. Therefore, I used a pre-trained mobile NetV2 instead of training a deep network from scratch. All images were resized to 224 by 224 pixels and normalized. Standardized pre-processing improves numerical stability and training convergence. To increase robustness, I applied data augmentation techniques such as rotation, shifting, zooming, and horizontal flipping. These transformations simulate real clinical variability and help reduce overfitting. I used mobile NetV2 with ImageNet weights as a frozen feature extractor. On top of the space, I added a lightweight classification net including global average pooling, dense layers, dropout, and the softmax output for 3 classes. I split the data into training, validation, and test sets and used ADAM optimization with early stopping to prevent overfitting. The model achieved 86.08% accuracy on unseen test data. The training and validation loss curves show minimal divergence, indicating good generalization performance. The confusion matrix highlights an important limitation. 18 malignant cases were misclassified as benign, which represents a critical clinical error. This indicates a conservative bias toward benign predictions. Recall values further emphasize this issue. While benign recall is high, malignant recall is the lowest. This increases the risk of false negatives, which is unacceptable in real clinical scenarios. The main limitations are class imbalance and the fact that segmentation masks were not used during training. In future work, malignant sensitivity can be improved using advanced loss functions and deeper fine-tuning. In conclusion, this study demonstrates that transfer learning is an effective baseline, but further improvements are needed for safe clinical use.